In this question, we were asked to find the maximum for each and every contiguous subarray of size k. Here we were given that k is equals to 3. Now we'll follow some DQ operations such that the answer for every subarray will be present at the head of the DQ. Then the first operation will be, before pushing something into the DQ, we'll check whether the back of the DQ is smaller or not. If it is smaller, then we'll just pop back until we find something bigger or the DQ gets empty. Now the second rule would be, while changing the subarray from there to there, we'll just check whether the front of the DQ, that is the answer for the previous subarray, is valid in the new subarray or not. That is checking the index present at the head of the DQ. Is one of the index present in the new subarray or not? If it is not, then just pop front. By doing that, we can get the answer for each and every subarray very easily. Thank you.
try to understand it, and we will also see the implementation side by side in the next lecture. Hi everyone. In this lecture, we will talk about a very famous algorithm for computing shortest paths on weighted graphs. So this algorithm is known as Dijkstra's algorithm. So let us dive into this algorithm, try to understand it, and we will also see the implementation side by side in the next lecture. So let's talk a little bit about shortest paths. Okay, so we have seen that graphs has many applications. One such application is finding shortest paths. Okay, everyone uses apps like Google Maps. These applications also give you the shortest path. Suppose you want to go from one location to another, and maybe there are multiple routes, you don't know which one to pick. So it may suggest, okay, you should go via this route. This route is the one that is shortest. Okay, so what we need to do is we need to come up with an algorithm that help us to find the shortest route between a source and a destination. Okay, this algorithm is a single source shortest path algorithm. That means starting from any position, it will give us the shortest distance to all other nodes that are there in the graph. Let us say this is the graph, and it will tell us, okay, if you want to go to this node, then uh, this route is going to be the shortest one. Okay, maybe from here to here. So what we will take input, we will take input a graph and a single source from which the distances to all other nodes will be computed, including the destination node. So this is the meaning of single source shortest path algorithm. And the graph is a weighted graph because two nodes are connected by some road, or there is some cost associated with traveling from one point to another, and these costs can be different. And if all of these costs are same, then it becomes a simple case of shortest paths in a undirected graph, which we have already seen how we can solve that problem using breadth first search. But now let us focus on how we can do it for weighted graphs. So this is an example of weighted graph, and I want to find out the shortest path from 0 to all other nodes. Okay, so 0 I'm taking as a source node. So this is the source node. So what this algorithm says is, in the beginning we do not know the distance to any of these nodes. Okay, so let us maintain a distance array, and in this we are going to store the distance of all the nodes. So 0, 1, 2, 3 and 4. So 0 is at distance 0, the source node. Rest all the nodes are at infinite distance, so we put these distances as infinity. We don't know. Okay, so now what you can do, starting from 0, you can visit 3 nodes. Okay, so 0 is there, and we will also do one thing. We will also maintain some kind of a data structure where we are noting what are the nodes that we have currently explored. So let us see. So we are currently in a, this data structure that we are going to use is going to be a priority queue or a set, but I'm going to use a set. Okay, I will tell you why. So what I have done in this set, I have added one node that is 0, and its distance is also 0. So set keeps the nodes sorted according to some property. So that property in our case will be distance. So you will come to know why we are going to put these nodes in the set also. Okay, So like when you do level order traversal, you maintain a queue, but here all the edges have different weights. So we want those nodes which have a lesser distance, they should come to the front of the and set will help us to ensure that this property is being maintained. So in the beginning we have visited only one node, that is the source node, and it is inside the set. So what we will do, we will remove this node from the set. Okay, so this is the node index, and here it is distance. So set is going to store a pair, okay, pair of intent type of stuff. So what we do, we remove this and we say okay, from 0 we can go to this node, that is 1, and we see okay, can I update the distance of 1? Yes, because distance of parent is 0, this edge is 1, so it is going to become 1, and it is less than infinity, so I update this distance as 1. Okay, and I also put this inside the set. Distance is 1 and the node is also 1. Okay, this goes inside the set. What other node I can explore? I can go to 2. So I pick this edge. I say okay, 0 plus 4. This distance is 2, which is less than infinity. I update this distance of 2 and I put this node inside the set. Okay, and I can also go to 3. So I can say okay, 3 has a distance 7 now, and I put this inside the set. Now what is going to happen? Out of the 3 nodes you have, which one you're going to pick? Since it's a greedy algorithm, and it also makes sense to pick the node which has minimum distance till now. So you will pick the node 1. Okay, you will remove it from the set because it is finalized, and you will try to update other nodes. Doesn't matter whether they are visited or not, but they are not finalized yet. Okay, you will try to update other nodes. Okay, and you're going to try to update their distances. So what you're doing, 2 now has a distance of what? 2 has a distance of 4. Okay, and 3 also has a distance of 7. So from 1 you can see I can go to actually 2. Okay, following this edge I can go to 2, and what is the distance I'm going to have? So distance of 1, that is 1, plus this edge, that is 1. This distance is 2, which is lesser than what distance I already had in the set. So I'm going to update this distance as 2 in my distance array, and also in the set I'm going to update this pair. Okay, I'm going to say let us update this pair, but in the set you don't have any such feature like update. So what we will do, in order to do an update, we will delete the old entry and we will do a new insertion. Okay, so that will behave like a update. So we will delete this and we will insert a new entry, and since set is going to keep the things sorted, so this is how the new set will look like. So you have a node 2 which is at a distance of 2, and you have a node 3 which is at a distance of 7. This is how the set will look like after this deletion and the insertion operation. Okay, and any other node you can visit? No, you cannot visit any other node. Now in the set you only have these 2 entries. Which one is the minimum? This one is the minimum. So you pop this out, that means you're finalizing the node 2, and from 2 you're trying to visit the nodes which are not yet finalized. So you can visit only 3. If you go via this route, so that will become distance of 2 is 2 plus 2, this distance is 4. So what you do, you update this distance as 4. Okay, and in the set you say okay, let me remove this entry and let me put a new entry 3 and 4. Okay, and this one is already gone. So 3 has now a distance of 4, and in the set you only have now one entry. There is no other node on which you can go. So this is now finalized. You pop this out and you try to update nodes which are connected with 3 and not yet finalized. So you go to 4 and you say okay, this distance is 4, and now I can say 4 plus 3, this distance is 7, which is less than infinity. So you push this inside your set. So 4 is at a distance 7, that's what you get. And in the end you will see I will remove this node from the set and your set will become empty, and you will finally have these distances as the final distances. Okay, so if we look at So going via this route, 1 has a minimum distance of 1, 2 has a minimum distance of 2, 3 has a minimum distance of 4, and 4 has a minimum distance of 7. This is what we have in the distance array. So this is what Dijkstra's algorithm is all about. It's a very simple, very intuitive algorithm. Hi everyone. So in this lecture we will discuss how we can implement the extras algorithm that we have just discussed. So we have this graph which is Hi everyone. So in this lecture we will discuss how we can implement the extras algorithm that we have just discussed. So we have this graph which is created here, and now we will build this function int dijkstra's which will return the length of the shortest path from any source to a particular destination that is being given in the input. So let's see how we can do this. So as we discussed, in order to implement this algorithm, we need two data structures. One is a visited array that we can create using a vector. So visited of bool, vector of bool, which is visited for v vertices, and everything is set to false in the beginning. And another thing that we need is a set. So set will store pairs. Each pair will denote the current node and its distance. So let's call this as S. The first step would be to initialize the distance. uh, Sorry, yeah. So what we can do, instead of taking the visited array, we can actually take the distance array and we can actually make it integer. And if the distance is infinity, we can simply say this distance is going to be int max. Okay, so this distance array will serve two purposes. One, it will tell whether a node has been visited or not, and if it is visited, then what is the distance. Okay, so int max denotes it is not visited. So in the beginning, we can say distance of source, that is the node itself from let's say this node from itself is going to be 0, and we are also going to insert a pair inside the set, so that will initialize the set. So we can say s dot insert, and here we can create a pair. So distance is 0 and the node is source. This is how we are going to initialize it. Next step would be to pop out one pair from the set and do some work. So we can say while s is not empty, let us see what is there at the front of the set. So I can say auto it equals s dot begin. This function returns an iterator, and using that iterator I can access two properties. One is the node. Node would be it arrow second, and its distance. So node distance would be it arrow first, because the first thing that I'm pushing in the set is the distance. Okay, and what we are going to do, we are going to remove this from the set. So I can simply say s dot erase it. So that is equivalent of pop operation. So we are accessing what is there at the front of the set, and we are removing it, and also we are copying the values inside two variables. One is the node and other is the node distance. Now what is the next thing? We need to iterate over the neighbors of node. So we can say for auto sum j, that is equal to okay, so let me just change the notation little bit. So I will call it as neighbor pair. For every neighbor pair that is there in adjacency list of node, we are going to do some work. Okay, so if it is not clear, let me just recap the code what we have written till now. So what we have done, we have created a distance array, and we have created a set which is empty, and we put the 0th node, okay, in the set. So we say, okay, this node is going to have a distance 0, and we are putting this node by making a pair. We put 0 comma 0 here. Okay, so what we do, while set is not empty, we remove something. So that part is done here. So we see what is there at the beginning of the set, and we say, okay, node is it arrow second, that is this value is the node, and it arrow first, this is what we have as the distance covered till now. Okay, so if I reach this node, then its distance would be, let's say, 1. Okay, so I can say, okay, this distance till now is 1, And from here, if I go here, so I can say, okay, if I take this edge of length 1, so that will be distance covered till now plus this length, that is the current edge. So let us change notation little bit. I can say this node distance is actually the distance till now that we have covered while reaching this node. Okay, and you can also call it as node distance, but this makes it little more clear. So what we are doing, we are iterating over the neighbors of a node. Okay, for example, maybe 0 has 3 neighbors, 1, 2 and 3. Okay, so we are iterating over the adjacency list, that is L of 0, and these have information stored like 1 1 and 4 comma 2 and 7 comma 3. So these are the weights and these are the nodes. So we are going to iterate over this list and we are going to see what we can do. So let's do some work here. So I can say int neighbor will be nothing but neighbor pair dot second, and int current edge, that means that would be neighbor pair dot first. So I'm trying to find out this length. Okay, so this length is 1, this length is 4, this length is 7. So I'm going to say this is whole entity is neighbor pair, and dot second gives me the node name, and dot first gives me the length of the edge that we are taking to reach that particular node. So what we need to do, we need to find what is the distance to reach that node if we take this particular edge. So we can check if distance till now, that is the distance to reach the parent of the current node plus the current edge, if this is smaller than whatever distance we have computed for these nodes. So now these distances are infinity. Okay, now these distances are infinity. So if we check if this is less than whatever distance we have computed for this node, we should update it. Okay, so how do we update it? We simply say distance of neighbor is equal to distance till now plus the current edge, and we insert these pairs inside our set. So we say okay, s dot insert make pair, and here we say distance of neighbor, that is the distance, and the node. Okay, so we're making a pair of two values, or you can use curly brackets to make the pair, that is also fine. So we are inserting that pair inside our set. So what we did, we inserted these elements in the set. We inserted 1 comma 1, 4 comma 2 and 7 comma 3, and they are sorted according to the distances, which are these values. So now one more step we have missed is we also need to remove if such a pair already exists. Okay, if for a node, if a pair already exists in the set with the old value of distance, then we should also remove it. So let's, because we wanted to do an update. Okay, so for these values, they are going into the set for the first time, it is perfectly fine. But now when you're going to pick this edge next time, this distance becomes 1. You're going to pick this edge and you're going to look at 2. 2 already has a distance of what, 2, and this already has a distance of 7. So when you're going to pick this edge, okay, you will see, okay, 1 plus 1 is now 2. Sorry, this distance is currently 4. Okay, this distance is currently 4. So you're going to look, okay, the node 2 is already present in the set. I want to update it. I want to make this distance as 2. So what you do, you remove this entry and you insert a new entry like 2 comma 2. Okay, this is what I want to do. So remove if a pair already, if a node already exists in a set. Remove if node, or if neighbor already exists in the set. So we are going to remove the old value of the distance. Okay, this may be true for some of the nodes, or let's see. So we can say auto f s dot find. We are going to check if that node exists in the set or not. So we are going to say, okay, find a pair whose value is distance of neighbor and the node indexes neighbor. So we are finding this pair 2 comma 4 because currently it's it is denoted using this distance of neighbor and neighbor. This is the node name and this is the distance, and this whole thing is inserted as a pair inside the set. If this value is not equal to s dot end, that means it is present in the set, then we are going to remove it. So s dot erase f, and we are going to insert the updated value with the new distance. Okay, so this goes inside the set. This is what we have done here, and that's it. Finally, once you're out of the loop, you can simply return the distance of destination. So you return distance of destination. If you want, you can also see uh, single source shortest distance to all other nodes. So maybe I can say for int I equals to 0, I less than v, I plus plus. I can say see out node is I, and you can see build is successful. And you can see build is successful now, and let us try to run this code. All here has a distance 0, 1 is at 1, 2 is at 2, the node 3 is at distance 4, and node 4 is at distance 7. So you can see we are getting the shortest path to all other nodes. Okay, so if it is still not clear, we can do a dry run on our example now. So let's see, in the beginning what I had distance of source node as 0, so this distance is 0. In my set I have 0 comma 0 as a pair. Then I say okay, extract what is there at the beginning of the set. I just remove this entry, and I know what is the node is 0, distance till now is also 0. I say okay, what are the pairs? So first pair I get is this one, and I say okay, this distance is infinity. So if I pick this edge, I can reduce this distance. I check distance till now, which is 0, plus the current edge 1, it is less than infinity. So what I do, I check whether this pair 1 comma infinity exists in my set. The answer is no. So simply this part is skipped. So we create a new pair and we insert 1 comma 1 inside the set. And then similarly we check whether this 2 comma infinity exists in the set. The answer is no. So what we do, we insert 2 comma 4 inside the set, or 4 comma 2 inside the set, and similarly we insert 7 comma 3 inside the set. But now what we do, we remove what is at the beginning of the set. We have this at the beginning of the set because this value is smaller. So we remove this thing and we try to update the neighbors. So neighbor is this, and we check whether there is something that is 2 followed by its distance. So distance followed by 2. So distance is what? Distance is 4. Whether this thing exists in the set, the answer is yes. So we first remove it, so this value is gone, and we insert a new pair, that is the distance till now, which is 1, plus the current edge, which is also 1, that is 2. So insert a new pair, that is 2 comma 2 inside the set. So this value now becomes 2. Now we look at what is at the beginning of the set. Again we get this entry at the beginning of the set, and we see okay, what are the neighbors. So 2 can actually visit what? 2 can visit, because if you try to update these nodes, they will not get updated because this condition will never be true because their distance is already minimum. Okay, so it doesn't matter. So 2 doesn't do anything for 1, it doesn't do anything for 0, so 2 has a neighbor 3. Can we reduce the distance of 3 if we go via 2? The answer is yes. So distance till now is 2, current edge is 2, distance of neighbor, distance of 3 was 7. Is it less than 7? The answer is yes. So we update, we see if 3 comma 7, if 7 comma 3 is there inside the set, the answer is yes. We remove it and we insert the new value. The new value is 4 comma 3. So we insert 4 comma 3 inside the set. So this value is there. Okay, and finally we remove 4 comma 3 from the set and we try to update this value, that is 7 comma 4. Okay, so this goes off and we try to update its neighbor, that is 7 comma 4. Finally this goes off and set is empty, and this is how you get this node, this distance as 7. So I hope this length of and discussed